Alright, well, welcome back. We're going to make another video here on the helpful hints on homework number 7. Problem number 1 states this: let f be a field and let f of x, g of x, n of x, k of x, and h of x be polynomials in f adjoint x. If f of x is congruent to g of x mod n of x, and h of x is congruent to k of x mod n of x, where the degree of n of x is greater than 0, then f of x plus h of x is congruent to g of x plus k of x mod n of x. Again, we hope you're finding the pattern on these things from the integers of modulo n of chapter 2. Now we're dealing with polynomials, so you've got to be very specific in terms of your wording. But so let's start off with the givens. This particular problem, again, this is a scrap sheet of paper here. This is not my official write-up of this problem, but the first one that's given is that f of x is congruent to g of x mod n of x. And while you're at it, the other thing that was given was that h of x is congruent to k of x mod n of x. Okay? And so I can, since they're both being modded out by n of x, I can use the same definition. So this will be by definition of congruence modulo n of x. You can't just say by definition of congruence. You got to finish it up by congruence modulo n of x, because there's a lot of different kinds of congruences out there. So you got to actually say which congruence you're doing. We're using modulo n of x. But what this means is that n of x divides f of x minus g of x, and n of x divides h of x minus k of x. Now remember, you don't get to use the divide symbol, but this is my scrap sheet of paper. And then I can go after the by definition of divides, which means that there exists polynomials w of x and v of x, elements of f adjoint x, such that f of x minus g of x is equal to n of x times w of x, and h of x minus k of x is equal to n of x times v of x. I got myself an equation. So, what do we want to show? In this problem, it says the part then, that's what you want to show, f of x plus h of x is congruent to g of x plus k of x mod n of x. What I want to show is exactly that. F of x plus h of x is congruent to g of x plus k of x mod n of x. What does it mean to show this? Well, again, from the definition of congruence modulo n of x, this means that n of x divides f of x plus h of x minus g of x plus k of x. And then by the definition of divides, remember, you don't get to abbreviate on any kind of things you turn in, but this is a scrap sheet of paper. This means that I want to show f of x plus h of x minus g of x plus k of x is equal to n of x times some polynomial. That's what I'm after, is that equation, because I can, once I get that equation and show that some polynomial, by definition divides, and divides this guy, and then by definition congruence, I work my way back up to what I want to show. So it's a two-step definition process. So the big question is, how am I going to get this guy here? Well, if you look at it, f plus h minus g plus k is equal to n times some polynomial here. So really what I want to do with these two equations to get that f plus h is I want to add these two equations together. So you would start that out by saying, well, as f of x minus g of x plus k of x, h of x minus k of x is equal to n of x times w of x plus n of x times v of x by substitution. Then you could factor out your n of x over here, and on this side over here, because remember, f is a field. F's a field, but when you adjoin that x, f adjoined x is going to be an integral domain because x is not a unit, so it can't be a field, but it's still a commutative ring with identity. And it doesn't have any zero divisors. These are polynomials. Polynomial times a polynomial equals 0 means that either the first polynomial was 0 or the second polynomial was 0 because the coefficients are coming from the field. So this is an integral domain. And being an integral domain, you have commutativity, so I can distribute, I can factor out the negative out of it, and then factor out the n of x. So by the property of integral domains, you can manipulate by taking this polynomial plus this polynomial with your substitution and be able to turn it into this guy. So let's take a look at number 2 then. Number 2, again, the key to it is catching the patterns, but on this one, it says this. Let f be a field, and let d of x, r of x, s of x, and t of x be polynomials in f adjoined x with r of x of positive degree. Show that if d of x is equal to the GCD of r of x and s of x, and there is a polynomial k of x element of f of x such that s of x times k of x is congruent to t of x mod r of x, then d of x divides t of x. So again, let's start off with the givens. What's given in this first part is the fact that the d of x is equal to the GCD of r of x and s of x. And so, remember with the GCDs, you really have two options. And we've got to figure out which option we need to use. So, we have by the definition of GCD option, and then we have by theorem 4.8 for polynomial GCDs option here. By definition of GCD option, this tells you that d of x divides r of x, and d of x divides s of x. And by definition of divides, there exists polynomial, we'll call them u of x and v of x, elements of f adjoined x. Okay, so d divides r, so r is going to be bigger. So we have r of x is equal to d of x times u of x, and s of x is equal to d of x times v of x. So I have the divided equations. The other option is theorem 4.8. Theorem 4.8 says that there exists, I'll use the same guys here, polynomials u of x and v of x, elements of f adjoined x, such that you have here r of x times u of x plus s of x times v of x is equal to d of x. You have a big equation. So we don't know which option to take yet, but let's keep going here. Also given, you were given that s of x times k of x is congruent to t of x modulo r of x. Well, what does that mean? That means by definition of congruence modulo, this time it's r of x, we have r of x divides s of x times k of x minus t of x. And then by the definition of divides, there exists a polynomial w of x, element of f adjoined x, such that s of x times k of x minus t of x is equal to r of x times wx. Again, I got a big equation, so I'm always kind of circling my equation because this is the algebra part of the modern/abstract algebra thing. So now here's the big picture. What do I want to show? In this problem, I want to show that d divides t. d of x divides d of x is polynomials. So won't you show d of x divides t of x? Well, this means that by definition of divides, that I want to have t of x is equal to d of x times, and this is the world of polynomials, some polynomial there. I got to figure out who the polynomial is going to be. But what I really need is I look at this. I need a big equation with t of x equals. Well, these guys up here don't have t of x equals, but this one does. This one at least has a t of x in it. So, as s of x times k of x minus t of x is equal to r of x times w of x, where all these polynomials came of f adjoint x, I believe you can sit there and solve this thing for t of x by adding t of x to both sides and subtracting r of x times w of x. Because remember, f's a field. Once you attach x onto it, it makes it an integral domain. It's a ring, but it's stronger than that. It's an integral domain. So I have commutativity, I have no zero divisors in it, but you can do all the algebra you need to do. So you can solve for t of x, and if I solve for t of x on this guy, I end up getting t of x is equal to s of x times k of x minus r of x times w of x. I want to be able to factor out a d out of this guy. So back to my definition of GCD and my theorem 4.8 guy. So which one should I take? Well, do I need a big equation with d of x equals into it? No, I want to be able to divide by d of x. So I don't want the big equation. So don't go here. Go here. The definition of GCD gives me these little bitty equations that I can substitute. So I can sit there and substitute in for the r of x and s of x. So you end up getting t of x is equal to the s of x is d of x times v of x. Multiplied by that k of x minus the r of x was equal to, up here, r of x is equal to d of x times u of x. And then that's by the substitution. And then I can factor out that d of x. And I believe you can figure out what your polynomial is going to be. But remember, as always, the reason why this guy's a polynomial is since v of x, k of x, u of x, and w of x are polynomials, then u of x times k of x minus v of x times k of x minus u of x times w of x is a polynomial in f adjoint x because f adjoint x is an integral domain. You have that closure property. And then you can work your way up by definition of divides. So look at the strategy. And the other strategy is you've seen problems like this before, but the last time you saw them, everybody was an integer. Now they're polynomials. Okay, well, the last problem, you were supposed to find all the equivalence classes in Z3 adjoint x modded out by P of x, where P of x is equal to 2x cubed plus 1. Well, when you do Z3 adjoined x modded out by a polynomial 2x cubed plus 1, you're going to get this set of equivalence classes, which makes a ring here. But what would the equivalence classes look like? Remember, just like with that Z mod in, it's what you're modding out by. What you're slash dividing out by is going to be what the equivalence classes look like. So for this particular one, we're modding or dividing out by an x cubed. And the pattern on the equivalence classes, modulo P of x and stuff, is the degree. And it's always got to be the remainder of what you're dividing out by. So if you divide by an x cubed polynomial, the biggest polynomial you can have for remainder is a quadratic, always a degree 1 less than the actual degree. So a degree 1 less than 3 would be 2. A degree 2 polynomial is the famous quadratic, ax squared plus bx plus c, where a, b, and c are elements of Z3 because that's where your field comes from. And remind you, Z3 are the elements 0, 1, and 2. Notice my coefficients, my polynomials can only be 0, 1, and 2. There's no negative 1, there's no 45, there's no anything bigger or anything negative. You got to be 0, 1, and 2. Now, once you get beyond that, you can always bounce him back into that world of Z3, 0, 1, and 2. So, first off, how many equivalence classes am I going to find? Well, A has 3 options, 0, 1, and 2. B has 3 options, 0, 1, and 2. C has 3 options, 0, 1, and 2. And the multiplication principle, 3 times 3 times 3, there are 27 equivalence classes. And the trick on doing the 27 equivalence classes and running these guys up is you first start off with, for example, A equals 0, B equals 0, and then you run the gamut on C. You got to do it systematically. If you just happen to mindlessly look out there and try to gather all of them in your head by doing all the different combinations, you're going to miss one. This is only 27. Imagine if it was, like I said, I gave that a 4th degree polynomial, then it would have been a cubic, then there would have been 81 of these guys. And it's real easy once you get a lot of them to be able to miss them. So count when you're done, make sure you got them all. But the trick is doing it systematically. So if A equals 0, B equals 0, run the gamut on C. C could be 0, C could be 1, C could be 2. And then A equals 0, B equals 1, and then you run a gamut on C. So A is 0, so no x squared. B is 1, so that would be just x. And then run the gamut on C. X plus 0, x plus 1, x plus 2, and then you just keep on going. And then you start over here with, after you do these guys, A equals 1, and B equals 0, run the gamut on C, and you keep on basically running them all out. And when you're done, there should be 27 of these guys. All right. Now, once you get these guys, the next question, part B, is this particular ring, Z3 adjoined X, modded out by 2x cubed plus 1. The question is, what kind of ring is he? Is he a basic ring? Is he commutative ring with identity? Is he a commutative ring? Is he a ring with identity? Is he an integral domain? Or is he a field? What kind of ring is this guy going to be? Now, I could officially, if you wanted to prove your work and stuff like that, you could do it old school and do the multiplication table. But remember, you got 27 equivalence classes for this particular ring, and you're going to have 27 equivalence classes, so across the top and around the side, and then you can do your multiplication like we did before. That's great, but I don't want to do 27 equivalence classes because that makes this chart incredibly big, and that's kind of the point, is not to be able to have to actually analyze each individual piece of data and see if we got any zero divisors, make sure every non-zero element's a unit, stuff like that. Not looking for that. The easiest way was what we learned in section 5.3, and that is looking at the polynomial that you're modding out by. P of x equals 2x cubed plus 1. If this particular polynomial is irreducible, irreducible is prime-ish, so it acts like a prime, and when you mod out by a prime, remember you got fields, look at z mod 40, let's see here, get the prime one here, z mod 11, that makes a field. When you mod out by a prime integer, you get a field. But if you mod out by a non-prime integer like z mod 45, you get commutative rings with identities. The pattern is the same, except you look at your polynomial. If the polynomial is irreducible, that's prime-ish, you're going to get a field. If the polynomial is reducible, then you're going to get commutative ring with identities. So you never get basic rings out of this guy. You won't ever get an integral domain out of this stuff. You only got 2 options on it. It's either going to be a commutative ring with identity or a field, because these are polynomials where the coefficients come from the field, so automatically they commute. So the polynomials are going to commute. You're going to have the identity because one element's going to be inside your field, and basically all the other coefficients being 0, you get the 1 equivalence class, which pretty much acts as your identity. So every part's going to be there, except are you going to get 0 divisors or not? And if you don't get any 0 divisors, it's a field. If you get 0 divisors, it's going to be a commutative ring with identity. But the trick is this guy irreducible or not? And remember, to check for irreducibility, all you got to do is look and see if you got any zeros. Now, this is a finite field, so This is in Z3 adjoin X, so my elements in Z3 once again are the elements 0, 1, and 2. So I'm going to check 0, I'm going to check 1, and I'm going to check 2. And I'm going to see, do I get any zeros? So any of these numbers equate back to being 0 in Z3. If I do, I got a root. And if I have a root, that means my polynomial is reducible. If I don't have a root, none of these numbers will be equal to 0 in Z3, then the polynomial is irreducible. So that's kind of the trick on this particular problem to figure out what kind of ring it's going to be. So basically just fill out the blank once you did that, because this is the proof. And you stayed in there, you know, there are zeros, therefore the polynomial is reducible. That makes the ring a commutative ring with identity. Or there are no roots, therefore p of x is irreducible, therefore the ring is going to be a field. And there you go. So that's the proof is right in here. So I hope this has been helpful, and I'll see you guys on the next video.